Our universe might be the product of cosmic evolution. This is the mind-bending proposal of cosmological natural selection, a theory where universes compete, reproduce, and evolve just like living things. By the end of this exploration, you will see the cosmos through an entirely new lens, as a dynamic arena where black holes give birth to new realities. We are about to journey through 25 fascinating theories built on this idea, from the fine-tuning of physical laws to the ultimate fate of all existence. We will uncover why our universe seems perfectly set for life, and whether black holes are less destroyers and more cosmic mothers. What does it mean for our place in reality if the cosmos itself is alive in a grand, evolutionary sense? It all begins with a single, radical question. What if the universe is not a lonely, one-time event, but a single link in an immense cosmic chain of ancestry? This is the core idea of physicist Smolin, first proposed in his groundbreaking 1997 book, The Life of the Cosmos. Smolin looked at the strange perfection of our universe, its laws and constants seemingly balanced on a razor's edge to allow for stars, planets, and life itself, and he proposed a mechanism for how this could happen without a divine designer. His answer was evolution, but on the grandest possible scale. Smolin's theory hinges on a fascinating role for the most enigmatic objects in the cosmos, black holes. In his view, a black hole is not merely a dead end for matter and light. Instead, it is a cosmic womb. When a star collapses into a black hole, its singularity, that point of infinite density, might not be a true end. According to Smolin's mathematical models, that singularity could pinch off from our own space-time and blossom into an entirely new universe of its own, a baby universe budding from the old. This new realm would be born with its own set of physical laws, its own fundamental constants like the strength of gravity or the mass of an electron. But crucially, these laws are not random. They are inherited with slight variations like genetic mutations from the parent universe. This simple idea sets in motion a breathtaking process of cosmic natural selection. Imagine a population of early universes, each with different random laws. Most of these universes would be stillborn, their constants set in such a way that matter never clumps into stars or atoms never form. They would fade into nothingness, producing no offspring, but a rare few, by sheer chance, have constants that allow for the formation of massive stars and, ultimately, black holes. These universes successfully reproduce. Their black holes give birth to new baby universes, which inherit laws very similar, but not identical, to their parent. Over countless generations, this process selects for universes that are exceptionally good at one thing, making black holes. The laws of physics in such a universe would be fine-tuned, not for life, but for black hole production. And here is the profound connection. The very conditions that make a universe prolific at creating black holes, like the existence of long-lived stars, stable atoms, and the complex processes of stellar evolution, are also the conditions that make life possible. We are not the goal of the process, but a kind of cosmic byproduct. We exist in a universe that has been shaped by billions of years of cosmological evolution, a universe that is, in a very real sense, a champion at creating the very objects that give it immortality. Our finely tuned reality, then, might not be a lucky accident, but the inevitable outcome of a vast, branching tree of life, where universes live, die, and reproduce. This profound concept is often known by another evocative name, the fecund universe hypothesis. Fecund simply means fertile or productive, and that is exactly the image it conjures, a cosmos that is endlessly creative, endlessly giving birth to new realities. It frames our entire universe not as a solitary island of existence, but as one branch on an unimaginably vast and ancient evolutionary tree. Each leaf on this tree is a separate cosmos, born from the collapse of a star in a universe that came before. The mechanism is as elegant as it is staggering. When a massive star exhausts its fuel and collapses under its own immense gravity, it does not simply vanish into a point of nothingness. According to this hypothesis, the singularity at the heart of the newly formed black hole, that place where our known laws of physics break down, may not be a final state. Instead, it could act as a seed. Through processes like a quantum bounce or a tunnel through the fabric of spacetime itself, that singularity blossoms into an entirely new region of spacetime, a baby universe with its own distinct beginning. This is where the idea of cosmic heredity takes center stage. Just as a child inherits genes from its parents, this new universe inherits its basic blueprint of physical laws from its parent. The strength of gravity, the mass of fundamental particles, the number of spatial dimensions, all are passed down, but crucially, the inheritance is not perfect. There are slight variations, cosmic mutations if you will. One offspring universe might have a gravitational constant, a tiny fraction stronger. Another might have a slightly different value for the cosmological constant. Most of these mutations are lethal, resulting in universes that collapse instantly or expand so rapidly that no structure ever forms. But occasionally, a mutation produces a universe even more efficient at forming stars and black holes than its parent. Over an eternity of cosmic generations, this simple process of reproduction with variation leads to an astonishing outcome: a multiverse populated predominantly by universes fine-tuned for one ultimate purpose: to create more black holes and thereby more cosmic offspring. Our existence in a universe filled with stars, galaxies, and the potential for life becomes a testament to this grand, unconscious evolutionary drive. This process of inheritance is not perfect, however, and that imperfection is the engine of all cosmic change. Within the framework of cosmological natural selection, Heredity describes the remarkable fidelity with which a baby universe copies the core rulebook of its parent. When a new cosmos buds from a black hole singularity, it does not start from a blank slate. Instead, it receives a near-identical copy of the fundamental constants, the numerical values that govern the strength of forces, the masses of particles, and the very structure of spacetime. Think of it like a cosmic recipe passed down through generations, with the exact amounts of ingredients for gravity, electromagnetism, and nuclear forces carefully transcribed. This high-fidelity inheritance ensures stability. It means that a universe good at making black holes will likely produce offspring that are also good at it, maintaining a successful lineage across the eons. But without change, there can be no evolution. This is where the second critical concept, mutation, enters the picture. During the violent, quantum gravitational process of a black hole collapse and the subsequent bounce into a new universe, the transmission of these cosmic constants is not flawless. Tiny, random variations can creep in. Perhaps the strength of the strong nuclear force is 1 part in a billion stronger in the offspring. Maybe the cosmological constant, which drives the expansion of space, is slightly different. These are the cosmic mutations, the accidental typos in the grand recipe. Most of these mutations are disastrous. A universe where gravity is even a fraction stronger might collapse back on itself instantly. One where the nuclear forces are too weak might never form atoms at all. These are the stillborn cosmoses, the evolutionary dead ends that leave no descendants. But very rarely, a mutation proves beneficial, not for any conscious purpose, but in the simple, brutal metric of reproductive fitness. A slight tweak might lead to stars that form more efficiently, burn longer, or collapse more readily into black holes. That universe would produce more offspring than its siblings, and over countless generations, that advantageous trait would spread through the cosmic population. This endless cycle of heredity and mutation, of copying and occasional error, provides the raw material upon which natural selection acts. It transforms the multiverse from a static collection of random worlds into a dynamic, evolutionary landscape where universes compete in a purely unconscious way for the ultimate prize, cosmic immortality through reproduction. The ultimate measure of fitness in this cosmic arena is brutally simple. A universe that creates more black holes is a universe that leaves more offspring, passing its laws forward into the future. Black holes are not just features of our cosmos, they are the very engines of cosmic reproduction, the singularities that pinch off to become new beginnings. This creates an immense, unconscious selection pressure across eons of universal generations. Any random mutation in the laws of physics that even slightly increases the number of black holes a universe can produce gives that cosmos a tremendous evolutionary advantage. Over time, the multiverse becomes dominated by universes whose laws are exquisitely fine-tuned for one purpose: to manufacture these gravitational engines as efficiently as possible. Consider what a universe needs to be a black hole factory. It needs stable, long-lived stars, because only massive stars end their lives in supernova explosions that collapse into black holes. For stars to form, you need gravity to be strong enough to pull clouds of gas together, but not so strong that it crushes everything instantly. You need nuclear forces balanced precisely to allow stars to fuse hydrogen into heavier elements over billions of years, providing the long, stable burning necessary for planetary systems and the potential for life to arise. You need a cosmological constant, the energy of empty space, that is small enough to allow galaxies to form, but not zero. Our universe, it turns out, appears suspiciously optimized for this very task. The strength of gravity, the mass of the proton, the value of the cosmological constant, all seem poised on a knife edge that allows for a rich ecology of stars, galaxies, and ultimately, black holes. We live in a cosmos where supermassive black holes sit at the hearts of galaxies, where stellar mass black holes are scattered throughout the Milky Way. From the perspective of cosmological natural selection, this is not a coincidence welcoming life. It is the signature of a universe that has won an evolutionary race, a universe shaped by the relentless pressure to reproduce. This brings us to a deep and persistent mystery, one that has troubled scientists and philosophers for generations. Why does our universe seem so perfectly tailored for our existence? One prominent answer is known as the anthropic principle. In its simplest or weak form, the principle states a rather obvious fact: we can only observe a universe that is compatible with observers like us. It is a selection effect, like a lottery winner marveling at their own luck while ignoring the millions who lost. The weak anthropic principle does not explain why the universe is fine-tuned. It simply notes that if it were not, we would not be here to ask the question. It can feel like a philosophical shrug, a way of saying we are just incredibly lucky. For many, this is deeply unsatisfying, as it offers no causal mechanism, no story for how this improbable fine-tuning came to be. This is where cosmological natural selection presents a radically different answer. It does not accept fine-tuning as a brute fact or a staggering coincidence. Instead, it proposes a concrete, physical process that actively shapes universes toward the conditions we see. The key insight is a profound link. The same physical laws that allow for complex chemistry, stable planets, and ultimately life are also the laws that maximize the production of black holes. A universe that is good at making stars that live long lives, forge heavy elements, and then die in spectacular supernova to create black holes, is also a universe that is primed for the emergence of life. We are not here because of random luck, but because we are in a universe that has been shaped by a relentless, evolutionary pressure to reproduce. Cosmological natural selection transforms the anthropic principle from a philosophical observation into a scientific prediction. It says, of course, we find ourselves in a life-friendly universe, because life-friendly universes are a predictable byproduct of a multiverse evolving to produce black holes. It replaces the question of why we are so lucky with a testable hypothesis about cosmic heredity and mutation. This positions cosmological natural selection as a powerful alternative, one that seeks a cause within the laws of physics itself, rather than leaving fine-tuning as a miraculous accident or invoking untestable realms of metaphysics. A scientific theory must do more than explain what we already see. It must make bold, testable predictions about what we have not yet found. Cosmological natural selection stakes its claim on one audacious forecast. The fundamental constants of our universe are not random. They are precisely tuned to maximize the production of black holes. This is not a vague philosophical statement. It is a concrete mathematical target. If the theory is correct, then tweaking any constant, even slightly, should result in a universe that makes fewer black holes. Our cosmos should sit at a peak of black hole fecundity. From this central prediction flow several specific and potentially falsifiable consequences. For instance, the theory makes a sharp claim about the fate of the most massive stars. It predicts that the upper mass limit for a star to end its life as a neutron star, a dense ball of neutrons, is as high as physics allows. Why? Because any star that can possibly collapse into a black hole should do so. The dividing line between stars that become neutron stars and those that become black holes should be pushed to its extreme, maximizing the number of black hole progenitors. Similarly, the theory makes predictions about stellar physics and the processes of collapse. The properties of nuclear matter, the behavior of supernova, all should be optimized not for elegance, but for the efficient manufacturing of singularities. Now, critics rightly point out the immense challenge in testing these ideas conclusively. We cannot run experiments on other universes, and our observations of stellar collapses and neutron star masses are still evolving. A single measurement that contradicted a key prediction could weaken the theory, but confirming it requires showing our universe is optimal, a far more difficult task. Yet, therein lies its profound scientific value. By making such specific, falsifiable claims, cosmological natural selection lifts itself from the realm of pure speculation into the arena of legitimate scientific inquiry. It gives astronomers and physicists a new lens, a new set of questions to ask about the data they collect. Every new observation of a supernova, every precise measurement of a neutron star's mass, becomes a potential test of a cosmic evolutionary process. Yet for all its elegance, cosmological natural selection has faced intense scrutiny from within the physics community. The theory presents a breathtaking narrative, but critics argue it lacks the rigorous mathematical scaffolding required of a fundamental physical theory. One of the most significant challenges is the mechanism itself. While the idea of a black hole singularity birthing a new universe is compelling, the precise physics of how this happens remains speculative. Our current theories, general relativity and quantum mechanics, break down completely at the singularity, without a working theory of quantum gravity to describe those first moments of a new cosmos. The reproduction step exists in a conceptual limbo. It is a powerful metaphor, but can it be more than that? This leads directly to a second major criticism, the definition of cosmic fitness. In biology, fitness is clearly tied to reproductive success in a shared environment. But what does it mean for a universe to be more fit than another? Universes do not compete for limited resources in a common arena. They are likely causally disconnected from their siblings. Critics like physicist Leonard Susskind have argued that without a way to compare the total black hole output of different universes in a meaningful way, the concept of natural selection loses its explanatory power. It risks becoming a tautology, simply stating that universes that make more black holes make more black holes. Susskind and others have also accused the theory of being a just-so story, a narrative that sounds plausible after the fact but is not driven by predictive mathematical necessity. They contend that the apparent fine-tuning for black hole production could be a coincidence, or explained by other multiverse theories like eternal inflation, where an infinite variety of universes bubble into existence randomly, making our life-friendly one a statistical inevitability. This debate, however, is not a dismissal but a vital part of the scientific process. The criticisms force the theory's proponents to sharpen their ideas, to seek mathematical formulations and specific, falsifiable predictions that can withstand scrutiny. The controversy itself highlights how cosmological natural selection has succeeded in one crucial way. It has ignited a profound and stimulating conversation about the very nature of scientific explanation for the cosmos, pushing us to ask harder questions about origins, causality, and what a true theory of everything must ultimately accomplish. The cosmological constant is a number of profound consequence, a single value that holds the fate of all structure in its grip. Known by the Greek letter lambda, this constant represents the energy inherent in empty space itself, a mysterious force causing the expansion of the universe to accelerate. Its measured value is astonishingly small, but crucially, it is not zero. If it were even slightly larger, the story of our cosmos would be one of utter desolation. A more powerful lambda would act like a runaway engine of repulsion, causing space to stretch apart at such a ferocious rate that matter could never coalesce. Gravity, the great architect of the cosmos, would be overwhelmed from the very beginning. Primordial gas clouds would be torn asunder before they could ever collapse into the first stars. No stars means no galaxies, no heavy elements, and certainly no black holes. Such a universe would be a featureless, expanding void, a cosmic dead end in the evolutionary chain. Conversely, if lambda were negative, a possibility some theories allow, it would act as an attractive force, causing the universe to recollapse upon itself in a premature Big Crunch. Stars and galaxies might begin to form, but they would be snuffed out almost instantly, again leaving no time for a rich ecology of stellar life and death to generate many black holes. Cosmological natural selection provides a compelling narrative for why our lambda is the value it is. Through countless generations of trial and error, universes with lambdas too large or too negative were weeded out. They simply could not reproduce. Only universes with a lambda in a very narrow Goldilocks range, small enough to allow gravity to work its magic, but large enough to prevent a catastrophic early collapse, could successfully form the structures necessary for prolific black hole production. Our universe's accelerating expansion is not a random feature, but a finely tuned parameter, a dial set precisely to the setting that maximizes cosmic fecundity. We live in a cosmos whose very vacuum energy is optimized for one unconscious purpose: to create the conditions where stars can live, die, and give birth to new realities. But this evolutionary view of the cosmos forces us to confront one of the deepest mysteries in all of physics, the nature of time itself. For cosmological natural selection to be more than a metaphor, for universes to truly be born, live, and reproduce, there must be a sequence of events. One universe exists, it forms black holes, and from those black holes, new universes emerge. This requires a framework of causality, a before and an after that stretches across the generations of cosmic ancestry. This presents a profound philosophical challenge because our most successful theory of gravity, Einstein's general relativity, famously treats time in a very different way. In the block universe view favored by many physicists, all of eternity, the past, present, and future, exist simultaneously. Time is just another dimension, like space. In this timeless picture, the Big Bang and the distant future are equally real, just different coordinates. There is no true flow, no genuine becoming, just a static, frozen landscape of events. Cosmological natural selection fundamentally rebels against this idea. If everything is eternally fixed in a four-dimensional block, then there can be no evolution. Evolution is a process, a story of change and succession. Smolin himself is a passionate advocate for the reality of time. He argues that time is not an illusion, but the most fundamental feature of existence. For his theory to work, there must be a kind of meta-time, a higher dimensional temporal framework in which the entire life cycles of universes play out. In this view, each universe has its own internal time, but the multiverse itself has a history, a sequence where one universe gives rise to the next. This meta-time is not measured by clocks within any single cosmos, but by the causal order of creation itself, parent, then child. This perspective turns the block universe on its head. Instead of a timeless multiverse containing all possible cosmic histories, we get a growing, evolving network of causally connected realities, where each new universe is a genuine novelty, born from the past and influencing an open future. Cosmological natural selection, therefore, is not just a theory about black holes and constants. It is a stake in the ground in one of physics' greatest debates. It insists that time and change are real, and that our universe is not a frozen sculpture, but a living chapter in an unfinished story. This deep connection between time and cosmic evolution leads us directly to one of the most perplexing puzzles in modern physics, the black hole information paradox. For decades, this paradox has challenged our understanding of reality itself. According to quantum mechanics, information can never be truly destroyed. Every particle, every interaction, carries information about its past, and that information must be preserved, even if it is scrambled beyond recognition. Yet, when matter falls into a black hole, it seemingly vanishes behind the event horizon, destined for the singularity. If the black hole eventually evaporates through Hawking radiation, which appears to be random and featureless, what happened to all that information? Its apparent loss would mean the fundamental laws of quantum theory are wrong, a conclusion physicists are deeply reluctant to accept. Cosmological natural selection offers a breathtakingly speculative, yet elegant, potential solution. What if the information swallowed by a black hole is not lost at all? What if, instead of being destroyed, it is transformed? In the moment a black hole singularity gives birth to a new baby universe, perhaps the information from everything that ever fell into that black hole is not erased. Perhaps it is imprinted onto the very fabric of the new cosmos, woven into the initial conditions or even the fundamental constants of that offspring universe. In this radical view, the information becomes part of the cosmic genetic code. The history of a star, the composition of planets, even the faint echoes of civilizations that might have been consumed, all that data could be translated in some unimaginably complex way into the physical laws of a new reality. This idea creates a profound and poetic link between two great mysteries: the fine-tuning of our universe, which cosmological natural selection explains through evolution, and the preservation of quantum information, which the paradox demands. Our laws of physics, so seemingly perfect for creating black holes, might themselves be a kind of fossil record, a compilation of information inherited from a parent universe's entire history of cosmic digestion. It suggests that every universe carries within its DNA the story of its ancestors' demise. While this connection remains highly speculative and far from any testable proof, it illustrates the theory's power to reframe our deepest questions. It turns a paradox of destruction into a narrative of cosmic inheritance, where nothing is ever truly lost, only reborn in the laws of a new beginning. String theory presents its own vision of cosmic multiplicity, a vast and silent library known as the landscape. This is not a physical place, but a mathematical terrain of staggering possibility, where every valley and peak represents a different set of stable physical laws, a different possible vacuum state for a universe. The calculations suggest there may be 10 to the 500 or more such distinct configurations, each with its own values for constants like gravity and particle masses. In this view, our universe is just one page in an incomprehensibly thick book, its laws determined by a random quantum fluctuation during the birth of the cosmos. The landscape is fundamentally static, a frozen atlas of all that could be. Cosmological natural selection breathes life into this stillborn map. It does not just accept a random selection from the landscape. It proposes a dynamic process that actively explores it. Think of the landscape not as a library, but as a rugged, evolutionary fitness landscape. Each point is a possible universe, and its height represents its black hole production, its reproductive fitness. A random quantum fluctuation might drop a new universe onto any point, but only those that land on the high peaks, the configurations fine-tuned for making black holes, will survive long enough to reproduce. Their offspring, with slight mutations, will explore the nearby terrain. Over cosmic generations, this process of selection and variation would guide populations of universes toward the highest peaks in the landscape. This suggests a profound hybrid idea. Perhaps the string theory landscape describes the space of all possible cosmic blueprints, the raw genetic material. Cosmological natural selection, then, is the evolutionary engine that animates it, the process that selects which of those countless possibilities actually come to exist, thrive, and dominate the multiverse. Our universe would not be a random draw from a static catalog, but the current champion of an endless competition, its laws honed by eons of trial and error across the highest peaks of theoretical possibility. This evolutionary journey across the cosmic landscape leads to a powerful, almost poetic image. Our universe itself might be seen as a kind of organism, with its own life cycle mirroring those of living things on Earth. It begins with a birth, emerging from the singularity of a black hole in a parent cosmos. This is followed by a period of rapid growth and maturation, as the infant universe inflates, cools, and begins the intricate process of structure formation, weaving galaxies and stars from the primordial soup. Its adulthood is marked by stability and productivity, as generations of stars live and die within it, forging the elements and, most importantly for this theory, creating new black holes. This is the phase of reproduction, where the universe passes on its legacy. Finally, like all living systems, it faces an end, whether through the cold, eternal dissipation of heat death or a dramatic recollapse in a big crunch. The universe dies. But in doing so, it gives rise to new offspring, continuing the cycle. This analogy is compelling because it provides a narrative framework that feels intuitively familiar, transforming the abstract cosmos into something with a story, a beginning, a middle, and an end that is not truly an end, but a transformation. Yet, we must be careful with the limits of this metaphor. A universe does not have DNA in any biochemical sense. Its heredity is encoded in the immutable values of physical constants. Universes do not consciously compete for food or mates in a shared environment. Their fitness is measured passively by their output of singularities. They do not feel pain or desire, but the functional similarities in population dynamics are undeniable and deeply instructive. In a forest, trees reproduce by releasing seeds, and over generations, the forest evolves. In the multiverse, universes reproduce through black holes, and over cosmic generations, the population of cosmoses evolves toward greater fecundity. The analogy is not a perfect one-to-one mapping, but rather a guiding lens, a way to understand how selection pressures can shape reality itself, even in the absence of consciousness or traditional biology. It suggests that certain patterns, like birth, reproduction, and evolution, may be universal principles, appearing not just in the realm of the living, but in the very fabric of existence. Black holes may be the most dramatic cosmic parents, but they might not be the only ones. The search for other reproductive mechanisms pushes the theory into even wilder speculative territory, asking if the very fabric of reality might have multiple ways to give birth. One compelling candidate comes from the leading theory of the universe's explosive first moments, cosmic inflation. This period of faster-than-light expansion may not have been a one-time event. Some models suggest that inflation is eternal, with quantum fluctuations in the inflatoned field, the energy driving the expansion, constantly spawning new, bubble universes that pinch off from the parent. Each bubble could have different physical laws, determined by how the inflation field settles within it. This is a powerful reproduction mechanism already, but cosmological natural selection would add a crucial evolutionary twist. It would ask, what makes one inflating universe more fit than another? The answer could be its ability to produce the most baby bubble universes. The laws of physics in the parent inflating realm would be shaped by selection pressure to maximize bubble nucleation. Universes that inflate in just the right way, with fields tuned to bubble prolifically, would dominate the multiverse. Their offspring would inherit similar, slightly mutated inflationary potentials, continuing the evolutionary race. This shifts the focus from black hole singularities to the quantum foam of the false vacuum itself as a cosmic nursery. Another frontier lies within string theory's most ambitious extension, M-theory. Here, our entire universe might be a three-dimensional membrane, or brain, floating in a higher dimensional space. Collisions between such brains could be cataclysmic events of creation, each collision sparking a new Big Bang and a new universe with potentially different laws. Could natural selection act here? Absolutely. If some brain configurations or collision dynamics are more likely to produce new, stable universes, then those brain setups would, over a meta-time, become more common. The fittest brains would be those whose properties, like tension or vibrational modes, lead to the most fruitful collisions. Even the decay of a false vacuum, a quantum tunneling event where a region of space drops to a lower energy state, could be a reproductive act. If such a decay creates a new expanding universe domain, then universes where this quantum process happens more readily would leave more offspring. The unifying thread across all these mechanisms is the core evolutionary logic. It does not matter if the cradle is a black hole singularity, an inflationary bubble, a colliding brain, or a quantum fluctuation. What matters is the presence of heredity, variation, and a selection pressure tied to reproductive output. Cosmological natural selection is not wedded to one specific birthing process. It is a broader framework that could, in principle, animate any multiverse theory that allows for reproduction with inheritance. The question becomes not which mechanism is correct, but which one, if any, has shaped the laws we call home. This evolutionary chain, stretching back through countless generations of cosmic ancestry, inevitably leads us to a profound and ancient riddle. What was the first universe? If every cosmos is born from a black hole in a previous cosmos, we are faced with a cosmic version of the chicken and egg problem. What or where did the very first link in this immense chain come from? Cosmological natural selection, focused on the process of change, does not inherently provide an answer to the ultimate origin. Yet, it does reframe the question in fascinating ways, offering a few speculative paths through this primordial mystery. One possibility is that the chain extends infinitely backward, an eternal regression with no true beginning. In this view, there is no first universe, just an endless cycle of birth, death, and rebirth stretching into the indefinite past. Each cosmos is both an ancestor and a descendant, part of an unbroken lineage that has always existed. This mirrors some ancient philosophical concepts of a cyclic cosmos, but updated with the mechanism of black hole reproduction. Another path points to the strange rules of quantum physics. Perhaps the very first universe did not come from anything resembling a black hole or a parent cosmos. Instead, it could have spontaneously emerged as a quantum fluctuation from a state of absolute nothingness, a timeless void without space or laws. This singular, random event, a cosmic free lunch as some physicists call it, would have been the seed from which the entire evolutionary tree later grew. Its laws would have been random, but if they allowed for even a single black hole, the process of cosmological natural selection could begin, shaping all subsequent generations. A third, more radical idea blends these concepts. Perhaps our entire multiversal family tree is itself just one branch on an even grander, more ancient tree. The first universe in our line may have been born from a process we cannot yet comprehend, in a realm of physics beyond our own. By acknowledging it does not solve the ultimate origin problem, cosmological natural selection makes a subtle but crucial point. It shifts our focus from a singular, mythical beginning to the rich, dynamic history that follows. Instead of searching for one primal cause, we are invited to study the sprawling evolutionary tree of all existence, to trace the branches that led to our own finely tuned cosmos. The question changes from what started it all to how did it become what it is today. In doing so, it offers a new kind of origin story, not of a creation, but of a journey. The search for cosmic ancestors inevitably turns our gaze outward, to the silent expanse surrounding us. We have wondered for generations why, in a universe so vast and ancient, we have found no trace of other civilizations. This is the Fermi paradox, the profound and unsettling silence. Cosmological natural selection offers a startling, cosmic scale perspective on this mystery. If the laws of physics are fine-tuned for one purpose, to maximize black hole production, then life and intelligence are not the goal. They are, at best, a byproduct. In this grand evolutionary story, a universe could be spectacularly successful, filling itself with black holes, without ever producing a single conscious observer. Life might be an incredibly rare accident, a fleeting side effect of physics optimized for an entirely different outcome. Our loneliness would not be a puzzle, but an expected consequence of a universe shaped by unconscious, reproductive drives. The cosmos was not built for minds, it was built for singularities. We are simply here, fortunate to exist in a reality where the conditions for black holes also allow for the fragile chemistry of life. This view offers a humbling answer to why we might be alone. We are living in a cosmic machine designed for a purpose we do not serve, yet the story does not have to end there. Could intelligent life ever become relevant to this cosmic evolutionary process? Imagine a civilization so advanced it masters the physics of spacetime itself. Such a civilization might learn to engineer black holes, not from collapsing stars, but through technology. They could build them as energy sources, as computers, or as cosmic artifacts. In doing so, they would directly boost the reproductive output of their universe. A cosmos that spawns such a civilization would suddenly have a new, powerful mechanism for creating offspring. From the perspective of cosmological natural selection, this would be a monumental evolutionary leap. Intelligence would transition from a meaningless accident to a potent adaptive trait, a feature that increases the universe's fitness. Universes that, by chance, have laws allowing for the rise of such intelligence would out-reproduce those that do not. This paints a very different future, one where life becomes the universe's way of consciously ensuring its own reproduction. We are nowhere near such a capability, of course, but this thought experiment highlights a crucial point. The ultimate answer to the Fermi paradox might depend on which stage of cosmic evolution we are witnessing. Are we in a young universe where life is a rare fluke, or are we on the cusp of a new phase where intelligence becomes the engine of cosmic fecundity? The silence we hear today might simply mean we are among the first, or that the great cosmic engineers have not yet arisen. Or perhaps, most hauntingly, it means the universe's design has no need for them at all. This strange, impersonal driver for all of existence forces us to confront profound ethical questions. If black holes are not cosmic tombstones, but cradles, our entire relationship with them shifts. In many human cultures, places of death and birth are held as sacred, sites of profound transformation. Does the knowledge that a singularity might blossom into a new cosmos bestow a similar, awe-filled status upon a black hole? It would mean that the most destructive event we can conceive, the complete annihilation of matter and information, is simultaneously an act of supreme creation on a scale we can barely fathom. The death of a star becomes the birth of a universe. This perspective reframes cosmic death not as a final ending, but as a necessary metamorphosis, a painful but essential step in an endless cycle of renewal. It echoes ancient philosophies of cyclical time, but grounded in the stark mechanics of astrophysics. There is a deep, almost spiritual resonance in the idea that from the darkest voids, new light is born. Yet, this creative power is utterly indifferent. The black hole does not intend to create, it simply does, following the unconscious logic of physical law. This leads us to the most humbling implication of all, the concept of cosmic purpose. For generations, we have looked at the stars and wondered if there is a grand design, a meaning woven into the fabric of reality. Cosmological natural selection offers an answer, but it is one devoid of any comfort or special status for us. The multiverse may have a purpose, but it is not for us. The overarching goal, shaped by billions of years of unconscious evolution, appears to be the maximization of black hole production. It is a purpose of pure, blind fecundity. Our universe, with its beautiful spiral galaxies, its brilliant stars, and its life-bearing planets, is merely an exceptionally efficient machine for manufacturing singularities. We are not the point of the story. We are a fleeting, perhaps accidental, side effect of a universe built for a different kind of productivity. This can feel like a cold, even nihilistic revelation. Yet, there is a strange and terrible beauty in it as well. It suggests that creativity and renewal are fundamental properties of reality itself, built into the laws of physics. The cosmos is not static or dead. It is vibrantly, endlessly generative, driven by a simple, elegant rule: reproduce. Our own existence, our capacity for wonder and ethics, emerges from this vast, impersonal process. It means that the values we hold dear, like creativity, persistence, and the continuity of life, are not just human inventions, but reflections of a deeper cosmic pattern. We are not separate from this grand evolution. We are its momentary, conscious witnesses. This knowledge does not tell us how to live, but it might change why we look up at the night sky with reverence, seeing in the darkness not just an end, but the potential for a billion new beginnings. Our search for meaning in an evolving multiverse collides with another modern cosmic myth, the idea that our reality is a simulation. This theory suggests that an advanced civilization, perhaps in a parent universe, is running our cosmos as a complex computer program, a cosmic video game of unimaginable scale. At first glance, this seems to contradict everything cosmological natural selection stands for, replacing a blind, physical evolutionary process with a deliberate act of creation by intelligent designers. But what if these two radical ideas are not enemies, but strange allies? Consider the motivation of such a civilization. If they wanted to understand the nature of reality, to explore the vast landscape of possible physical laws, how would they proceed? Running random simulations, one after another, would be incredibly inefficient. A far more powerful method would be to implement an evolutionary algorithm, a program that generates universes with slight variations, selects the ones that meet certain criteria, and uses them to breed the next generation. This is precisely the logic of cosmological natural selection. In this speculative fusion, the black hole reproduction mechanism is not a fundamental law of a base reality, but the clever, optimized code of the simulation itself. The simulation is not designed to create us. It is designed to efficiently explore the parameter space of possible universes, seeking those with interesting properties like stability or complexity. The fact that we find ourselves in a universe fine-tuned for black hole production would be a direct result of the simulation's programming goal: to generate self-sustaining, fecund cosmoses that can run long enough to produce complex data. Our entire evolutionary history, from the first stars to our own questioning minds, could be an emergent phenomenon within a grand computational experiment. This perspective flips the simulation hypothesis on its head. Instead of asking if we are in a simulation, we might ask what kind of simulation would produce a universe like ours. A universe shaped by cosmological natural selection displays all the hallmarks of a brilliantly designed evolutionary algorithm, one that finds optimal solutions through variation and selection rather than top-down design. It is elegant, efficient, and requires no continuous oversight from a programmer. The cosmic code runs itself, exploring possibilities across eons of simulated time. This leads to a dizzying, almost paradoxical thought. Even if our universe is a simulation, the rules governing that simulation may themselves be the product of a deeper, more fundamental version of cosmological natural selection, operating in the civilization that built the simulator. The programmers might be using a tool they themselves inherited from an endless chain of cosmic evolution. Whether we are in a base reality or a nested simulation, the signature of this evolutionary process could be a universal constant, a repeating pattern woven into the fabric of existence at every level. It suggests that the drive to explore, to create, and to evolve might be the most fundamental law of all, whether the substrate is matter, energy, or pure information. But this grand vision of selection at the cosmic scale invites an even more profound question. Could the same principle be at work far, far smaller in the bizarre realm of quantum mechanics? A fascinating idea called quantum Darwinism suggests exactly that. In the quantum world, particles exist in a haze of possibilities, a superposition of many states at once. Yet when we look, we see only one definite outcome. Quantum Darwinism proposes that this transition from fuzzy possibility to concrete reality is not random. It is a process of selection. When a quantum system interacts with its environment, through photons bouncing off it or air molecules colliding with it, most of its possible states are fragile and vanish. Only the states that can create stable, redundant copies of themselves in the environment survive. These are the states we perceive as classical reality. Think of it like a message being whispered in a crowd. Only the clearest, most robust version of the message gets passed from person to person and survives. The environment selects for the quantum states that leave the most legible records. The parallel to cosmological natural selection is striking. In both cases, a process of selection weeds out the unstable and the unreproducible. In the quantum realm, the environment selects for states that can be copied. In the cosmos, the meta-environment of the multiverse selects for universes that can copy themselves via black holes. Reproduction and the creation of stable records are the keys to survival at both extremes of scale. This leads to a breathtaking, almost unified vision. Perhaps a form of Darwinism is not just a biological quirk of our planet, but a fundamental principle of reality, operating at every level. At the quantum scale, selection shapes definite reality from a sea of possibilities. At the biological scale, it shapes the incredible diversity and adaptation of life. And at the cosmological scale, it shapes the very laws of physics that allow the other two to exist. In this view, selection is the universe's most powerful algorithm, for generating order and complexity, from the spin of an electron to the spin of a galaxy. It is a single, elegant thread woven through the fabric of existence, suggesting that the emergence of stable, self-replicating patterns is not an accident, but the deepest tendency of nature itself. This thread of selection running through all of reality leads us to the ultimate mystery, the nature of consciousness itself. If Darwinian principles shape reality from the quantum to the cosmic, could they also govern the emergence of mind? This is perhaps the most speculative frontier of cosmological natural selection, a place where physics brushes against philosophy. Some thinkers propose a radical idea known as panpsychism, the view that consciousness is not a late-arriving product of complex brains, but a fundamental and ubiquitous feature of the universe, akin to mass or charge. In this view, even an electron might possess a faint, unimaginable glimmer of experience. If that is true, and if universes evolve, then a staggering possibility opens up. Could there be selection pressures not just for black hole production, but for the development of increasingly complex forms of cosmic consciousness? Imagine a universe where the structure of space-time itself, or the vast network of communicating galaxies, begins to exhibit organization reminiscent of a neural network. Such a universe might process information in ways we cannot fathom. If that complex organization somehow increased the universe's stability or its ability to create black holes, then over cosmic generations, universes with a tendency towards such conscious complexity would be selected for. Our own universe, with its intricate web of galaxies connected by filaments of dark matter, its stars forging the elements for life, and its planets giving rise to self-aware minds, might be an early step in this direction. We could be witnessing the universe not just becoming fecund, but becoming awake. This is, of course, deeply fringe speculation, far from any testable science. Yet, it is a fascinating logical extension of the core idea. If evolution operates at the cosmic scale, and if consciousness is a fundamental ingredient, then why couldn't they interact? It suggests a cosmos where the drive toward reproduction and the drive toward awareness might, in the longest of long runs, become intertwined. We are left to wonder if the silent, star-filled night sky is not just a nursery for new universes, but the sleeping cortex of a mind just beginning to dream. The most profound theories demand proof, and cosmological natural selection is no exception. While we cannot visit a parent universe, we might find its fingerprints in our own sky. Astronomers and physicists are now engaged in a cosmic detective hunt, searching for observational evidence that could support or shatter this radical idea. Their first clue lies in the oldest light in the universe, the cosmic microwave background. This faint afterglow of the Big Bang is a snapshot of the infant cosmos, and any anomaly in its smooth, cold uniformity could be a relic of its birth. If our universe was born from a black hole in a previous cosmos, that violent event might have left scars, subtle patterns, or asymmetries imprinted on the CMB like a birthmark. Teams analyzing data from satellites like Planck scrutinize this radiation for unexpected ripples, cold spots, or strange alignments that current inflation models cannot easily explain. Finding such a fossil record would be revolutionary, a direct whisper from our cosmic ancestor. The second line of inquiry listens for echoes in the fabric of space-time itself. Gravitational waves, ripples from the most cataclysmic events, could carry signatures of new physics. The merger of two black holes sends a specific chirp through the detectors like LIGO and Virgo. Cosmological natural selection suggests that black holes might not be exactly as standard physics predicts. Their interiors, or the very moment of their formation, could involve processes tied to universe creation. A subtle deviation in the gravitational wave signal from a merger, an unexpected ring or frequency, might hint at physics beyond Einstein, a glimpse of the reproductive machinery at work. Finally, the theory makes specific predictions about stellar death. It argues that nature should maximize black hole production, pushing the boundary between stars that become neutron stars and those that become black holes. Astronomers are now precisely measuring the masses of these dense stellar corpses, finding an overwhelming abundance of black holes at the very edge of what is theoretically possible, with very few heavy neutron stars, would align with the theory's evolutionary logic. This is not abstract philosophy, it is hard, empirical science. Each telescope observation, each gravitational wave chirp, each new map of the ancient sky is a test. We are sifting through the ashes of our cosmic origin, looking for a trace of the fire that came before. The universe may hold its history in the silent patterns of light and the tremors of colliding darkness, waiting for us to learn how to read its deepest story. The search for our universe's evolutionary fingerprints must account for its most dominant, yet invisible, components. Dark matter and dark energy together make up over 95% of the cosmos, and their mysterious influence could be the ultimate dials fine-tuned by cosmological natural selection. If the theory is correct, then the amounts and properties of these dark components are not arbitrary. They must be set to values that maximize a universe's ability to form galaxies, stars, and ultimately, black holes. Consider dark matter first, the cosmic scaffolding. It is the invisible glue that holds galaxies together. Without dark matter's gravitational pull, the ordinary matter from the Big Bang would have flown apart, never coalescing into the dense clouds that birth stars. A universe with too little dark matter would be a cosmic failure, a diffuse fog where stars are rare and black holes even rarer. A universe with too much dark matter, however, might face a different problem. Overdense regions could collapse too quickly and chaotically, forming monstrous black holes that devour potential star-forming material before orderly galaxies can take shape. The sweet spot, the amount that allows for the steady, prolific formation of galaxy after galaxy across cosmic time, would be strongly selected for. Our universe appears to have hit that precise balance, with roughly 5 times more dark matter than ordinary matter, a ratio that seems optimal for building the large-scale structures where stellar life thrives. But dark matter's role may be even more direct. Some speculative models suggest that certain types of dark matter particles could clump into ultra-dense cores in the early universe. These dark matter seeds might trigger the direct collapse of gas into supermassive black holes far sooner than standard models allow. In such a scenario, a universe's reproductive success would depend critically on the specific properties of its dark matter, the mass and interaction strength of its particles. A slight mutation in these properties could mean the difference between a universe that spawns a rich crop of early black holes and one that does not. Then there is dark energy, the force of cosmic acceleration. Its value, the cosmological constant, is famously fine-tuned. As we explored earlier, if it were much larger, no structures would form at all. But its precise value also influences the timeline of galaxy formation. A slightly stronger dark energy would have started accelerating the expansion earlier, cutting short the window for galaxies to assemble. A slightly weaker dark energy would allow more time. potentially leading to more galactic mergers and more opportunities to stir up gas and trigger star formation. The optimal value for black hole production likely lies in a very narrow range, allowing for a long, fruitful era of galaxy building before the accelerating expansion eventually pushes future star formation out of reach. The eerie coincidence that we observe both dark matter and dark energy in comparable amounts in our current epoch might not be a coincidence at all. It could be a signature of a universe that has evolved to extend its fertile period for as long as possible, maximizing the number of stellar generations that can live, die, and collapse into reproductive singularities. In this view, the dark sector is not just a mystery, it is the hidden evolutionary machinery. The fact that we cannot see or directly touch dark matter and dark energy becomes profoundly fitting. They are the silent architects, the parameters shaped by countless generations of cosmic selection to build a universe that is, above all else, fecund. The silent, mathematical elegance of cosmological natural selection has not remained confined to academic journals. It has escaped into the wilds of our imagination, inspiring storytellers who see in its logic a new kind of cosmic mythology. Science fiction, in particular, has seized upon this idea as fertile ground for narratives that are both intellectually rigorous and profoundly strange. Perhaps the most famous exploration comes from author Greg Egan in his novel The Clockwork Rocket. Egan does not merely mention the theory, he builds an entire universe and civilization from its premise. His story is set in a cosmos where the speed of light is not a constant, and the very geometry of space-time is alien. The characters, aware their universe is one of many in an evolutionary tree, race against time to alter the laws of physics themselves to ensure their cosmos survives and reproduces. It is a breathtaking application of the theory, turning abstract physics into the central drama of survival, where the stakes are the birth of future realities. This is the unique power of cosmological natural selection in popular culture. It provides a narrative engine as powerful as any epic fantasy, but grounded in a legitimate scientific hypothesis. Beyond novels, the theory has captured the imagination of popular science media, featuring in documentaries and podcasts that explore the biggest questions. Its appeal is undeniable. It offers a grand, story-driven framework for the cosmos, where other multiverse theories can feel abstract and impersonal. Cosmological natural selection feels like a saga. It has heroes of a sort, universes struggling to survive and reproduce. It has a clear plot, the evolutionary journey from random beginnings to finely tuned complexity. And it has a profound thematic resonance, blending the language of biology with the scale of cosmology in a deeply poetic way. We are familiar with the story of life evolving on a planet, but this idea asks us to contemplate life of a different kind, the life of spacetime itself. It transforms the cold, impersonal laws of physics into something that feels dynamic, historical, and almost alive. This narrative quality is why it sticks in the public mind. It answers a deep human craving not just for explanation, but for story, for a sense of place within a grand, unfolding drama. We are not passive inhabitants of a static stage, but active participants, however small, in a universe that is itself part of a vast, branching family tree. That is a powerful and hauntingly beautiful idea, one that continues to inspire wonder long after the equations fade from view. Yet this compelling narrative is not the only vision of a multiverse. Cosmological natural selection exists within a crowded field of ideas, each proposing its own version of reality beyond our horizon. To truly appreciate its unique perspective, we must briefly place it beside its most prominent rivals. The first is the inflationary multiverse, born from the theory of eternal inflation. Here, our Big Bang is just one bubble in a frothing, endless sea of spacetime. Quantum fluctuations in an eternally expanding parent vacuum constantly spawn new bubble universes, each with potentially different physical laws. This is a multiverse of staggering, infinite variety, but it is also a multiverse of pure chance. Our finely tuned laws are simply a random roll of the cosmic dice, one lucky ticket drawn from an infinite lottery. There is no reason, no cause, just the brute fact of probability across an endless ensemble. Then there is the many worlds interpretation of quantum mechanics. This suggests that every quantum decision, every possible outcome of a particle's behavior, actually happens, splitting reality into a constantly branching tree of parallel worlds. In one branch, you turned left, in another, you turned right. This multiverse is not about different physical constants, but about different histories unfolding from the same starting point. It is elegant, but it explains nothing about why the fundamental rules of the game are what they are. They are simply given. Finally, there is the most abstract of all, the mathematical multiverse. Proposed by thinkers like Max Tegmark, it suggests that every mathematically consistent structure actually exists as a physical reality. If a set of equations describes a logically possible universe, then that universe is out there, somewhere. This is a cosmos of pure logic, where existence and mathematical possibility are one and the same. It is breathtaking in its scope, but it offers no mechanism for why we find ourselves in this particular mathematical structure, and not another. So where does cosmological natural selection stand in this landscape? Its unique selling point is causality. It does not rely on infinite chance or abstract logic. It provides a specific, physical reason for our universe's properties. The fine-tuning is not an accident, nor is it a selection effect from an infinite array. It is the direct result of a historical process, an evolutionary chain of cause and effect stretching back through generations of cosmic ancestry. Our laws are not random, they are inherited and honed. This gives the theory a powerful explanatory edge. It answers the why, not just the what. It replaces the anthropic shrug, the idea that we just got lucky, with a dynamic story of adaptation. In a multiverse of infinite random bubbles, anything can happen, and therefore nothing is explained. In an evolving multiverse shaped by natural selection, the properties we see become not just possible, but probable, even expected. It transforms the multiverse from a static gallery of possibilities into a living, historical tree with a direction, shaped by the relentless, unconscious drive to reproduce. But a theory, no matter how compelling, must evolve or risk fading into mere philosophy. The future of cosmological natural selection hinges on a critical transition from a powerful narrative to a precise, predictive framework of mathematical physics. This is the great challenge and the next frontier. Proponents like Smolin are acutely aware that the theory's core mechanism, the birth of a universe from a black hole singularity, currently resides in a conceptual gray zone. Our equations fail at that point. To move forward, cosmological natural selection needs a home, a complete theory of quantum gravity that can describe the extreme conditions of a singularity not as an end, but as a transition. Smolin's own primary field of research, loop quantum gravity, is one promising candidate. Unlike string theory, loop quantum gravity attempts to quantize spacetime itself, suggesting that at the smallest scales, space is not smooth but woven from tiny, discrete loops. Crucially, Some models within this framework predict that a collapsing black hole does not create a true singularity. Instead, the immense gravitational squeeze is met with a powerful quantum repulsion, causing a bounce. That bounce could be the moment of cosmic birth, the precise mathematical instant where our universe's parent gave way to our own. If loop quantum gravity or a rival theory can successfully model this bounce and show how physical constants are inherited with slight variations, it would provide the rigorous backbone the idea desperately needs. The mathematics would transform a beautiful metaphor into a testable physical process. But the work does not stop at the chalkboard. The sky itself holds the ultimate verdict. Future observatories will be our guides, next-generation space telescopes, with vision far sharper than Hubble or James Webb, will peer deeper into the cosmic dawn, mapping the first galaxies and stars with unprecedented detail. They will test the theory's predictions about stellar populations and black hole formation in the infant universe. Was there an era of unexpectedly prolific black hole births? Did the first structures form in ways that suggest optimization for this singular purpose? Even more promising are the gravitational wave observatories of tomorrow. Projects like the Laser Interferometer Space Antenna, or LISA, a fleet of satellites designed to detect low-frequency ripples in spacetime, could open a completely new window. They might hear the whispers of primordial black holes merging in the darkness of the early cosmos, or catch the unique gravitational echo of a black hole's formation in a way that reveals something strange about its interior. A single anomalous signal, a chirp that defies the predictions of classical general relativity, could be the first hard evidence of physics beyond our current understanding, a potential fingerprint of the reproductive mechanism itself. Cosmological natural selection, therefore, is not a finished idea. It is a vibrant, developing hypothesis, a scaffold waiting for more beams and bolts. It lives in the tension between bold narrative and hard empirical proof, between the grand story of a fecund multiverse and the painstaking work of calculating a quantum bounce. Its future depends on this dual path, the mathematician's pen and the astronomer's eye working in concert. The theory asks us to be patient, to keep looking, and to stay open to the possibility that the next great discovery in astrophysics might not just tell us about our universe, but about its mother. This final idea is not just a theory about universes, but a revolution in how we think. Cosmological natural selection delivers a profound philosophical challenge to the very core of modern science. For centuries, the dominant approach in physics has been reductionism, the belief that to understand the whole, you must break it down to its smallest, simplest parts. Find the fundamental particles and the equations that govern them, and you will understand everything. This theory turns that logic on its head. It suggests that to understand the most fundamental laws, you cannot look only at the smallest scale. You must look at the history of the whole system. You must understand the cosmic life cycle, the story of birth, reproduction, and death across eons. It applies a biological paradigm, the logic of life, to the domain of cosmology. In doing so, it performs a breathtaking act of intellectual fusion. It blurs, or perhaps even erases, the line we have always drawn between the living and the non-living at the grandest possible scale. A universe that is born, that adapts, that reproduces, and that dies, certainly behaves in a way that feels deeply, undeniably alive. This is not saying the cosmos has a spirit or a mind, but that the patterns we associate with life, patterns of creativity, inheritance, and evolution, may be universal principles woven into the fabric of existence itself. The theory represents a monumental shift away from thinking of reality as a collection of static objects governed by eternal laws. Instead, it urges us to think in terms of processes, of evolution, and of narrative. The laws of physics are not timeless commandments etched on a cosmic tablet. They are more like traditions, passed down and slowly modified through generations of cosmic ancestry. They have a history, they have a story. This narrative approach to fundamental physics could pave the way for entirely new paradigms. It suggests that the ultimate theory of everything might not be a single, beautiful equation, but a set of rules for how reality learns and changes across time. It places our universe within a dynamic, growing family tree, forever connected to its past and responsible for its future. The legacy of this idea, therefore, extends far beyond astrophysics. It touches our deepest questions about what it means to exist, to change, and to be part of a reality that is not a static stage, but a living, breathing, and endlessly creative process. We are left not with a final answer, but with a new way of seeing, where every black hole is a question about our origin, and every law of nature is a page in an unfinished cosmic story. That journey through 25 theories has taken us from the cradle of black holes to the farthest reaches of a conscious cosmos. We have explored the staggering possibility that our universe is not a lonely accident, but a link in an immense chain of cosmic ancestry, shaped by the same evolutionary principles that govern life on Earth. The core idea of cosmological natural selection remains both simple and profound. Universes might compete, reproduce, and evolve, with black holes acting as cosmic wombs and the laws of physics as inherited genetic code. This framework transforms our finely tuned reality from a miraculous fluke into a predictable outcome of a grand, historical process. It reframes our deepest questions, offering not just a description of the cosmos, but an explanation for its most puzzling features, from the value of the cosmological constant to the eerie silence of the Fermi paradox. Whether this bold hypothesis is ultimately proven true or refined into something new, its true power lies in the expansion of our imagination. It provides a testable, physical narrative for the ultimate why, pushing cosmology beyond mere observation into the realm of cosmic history and causality. It reminds us that science at its best is not just a collection of facts, but a grand story of discovery, one that connects the quantum to the cosmic in a single, elegant thread. We want to hear which part of this journey resonated most with you. Was it the idea of black holes as cosmic mothers, the chilling cosmic purpose devoid of humanity, or the wild speculation about simulated universes and cosmic consciousness? Tell us in the comments below which of these 25 theories blew your mind the most. If you enjoyed this deep dive into the mysteries of space and existence, be sure to subscribe for more explorations that challenge what we think we know about